Hi again. The only thing that's missing in our analogy from electric fields, static, to magnetic fields is voltage or potential. There doesn't seem to be yet uh, a magnetic potential in all of this. And so that's what we're going to look at here in this video. And magnetic potential is kind of a cool thing. It's almost like a mathematical construct just to complete the analogy between electric and magnetic fields. But it's useful, of course. It's useful to help us calculate magnetic fields and magnetic flux, just like the electric potential, or just the regular potential, was useful in helping us calculate electric fields. So let us have a look at magnetic potential. Now, first of all, recall Maxwell's equations for static magnetic fields, and we had the divergence of B is equal to 0, and this says no magnetic monopoles. That one's really cool. The magnetic monopoles do not exist. For every north pole, you will find a south pole somewhere. That's pretty cool. It's not like you can isolate an electron or a proton, like you can do an electron and a proton. You cannot isolate a north or a south pole. All right, but this video is not about that. And remember the other Maxwell equation for static magnetic fields. This guy here. That might look a little bit different. I guess that's coming from, I guess we wrote it down like this before. The curl of H, the magnetic field intensity, is equal to the current density J. So remember the relationship between the magnetic flux density B and the magnetic field intensity H was that they're related by the permeability of free space, which is mu 0. Now, the idea is this, and we saw something similar with electric fields. We want to be able to solve these equations in general without relying on symmetry, or intuitive guessing like we did for Ampere's law. In electrostatics, we found the scalar potential V, voltage, and used it to find the electric field based on this fact here, that the electric field was the negative gradient of the potential. And then we could find the potential, and the potential was much nicer to use because it's a scalar, and then we could find the electric field, and also then we could apply boundary conditions like we did for Laplace equation and Poisson equation, where we just knew the voltage in two places, like on one on each boundary, and then we can find the electric field everywhere. So that's really useful. So we're going to try to do the same thing here. We're going to do something very similar for magnetic fields. Now, recall, and there's going to be a lot of vector, just a trigger warning here. There's a lot of vector analysis that you might recall, you might not recall. So the first thing that we need to recall, hopefully that you can remember, is that the divergence of a curl is 0, regardless of, so A right now is just some general field, I'm saying. So if we had some general field, if we took the curl of that field and then we took the divergence, we would get 0. And the reason for that is because curl and divergence are kind of opposites. Okay, so because that's the case then, and because the divergence of B is equal to 0, then we can write B as the curl of some vector field A. So we can say B is the curl of A. And again, why is that? Because if you put this into the monopole equation up here, then you'd have the divergence of the curl of A is equal to 0, and yes, that's always true. Now when you specify A like this, A is the curl of A is equal to the magnetic flux density, then we call A the magnetic vector potential. and it has units of Webers per meter. Now from Ampere's law, if we put this definition into the second equation up there, we have the curl of A is equal to mu 0 times the current density. Now there's another vector identity that we talked about early on in the term, and you're not expected to know it. That's okay, you don't have to memorize this, but you can go back to it if you want. The curl of A is this thing here. It's the gradient of the divergence of A minus del squared A. So that now is equal to mu 0 times the current density. All right, again, if you don't really recall that vector identity that I just applied there, that's okay. That's not the most important part of this video. Now, because B is obtained from A by differentiation, right? Del operator, the curl, is essentially differentiation. Then adding a constant to A doesn't change the physics of B. Think about your single variable calculus. Two functions can have the same derivative if they differ by a constant, right? So that is to say, if we add a constant to A here, it's going to have the same B. And even more latitude for vectors, you can not only add a constant to A, but you can add to A any field which is the gradient of some scalar field. Okay, and I'm going to prove that right now just to show you that. So suppose we have an A that correctly provides B for some situation. So that this is true in this box here. B is the curl of A. We ask ourselves, under what circumstances make some other new potential, maybe A prime, provide the same field B? So, maybe I have two A's, A and A prime, and maybe they give me the same B. How are they related? So just like, again, x squared plus 1 and x squared plus 3 have the same derivative, we're asking if A and A prime give the same B, how are A and A prime related? For single variable calculus, they're related by a constant. Okay, so what we're saying then is that, so here's our proof. We're saying that this new vector field A prime, the curl of it is equal to B, and so is the curl of A. We're trying to find out the relationship between A prime and A. So if that's true, then I can subtract the curl of A, and that's equal to 0 then, and I can factor out the curl operation. So this is the curl of A prime minus A equals to 0. But if the curl of a vector is 0, it must be the gradient of a scalar field, right? We said that in the beginning of this course. And so we're going to call that scalar field maybe lambda. Okay, so A prime minus A is equal to the gradient of lambda. Okay, because again, the curl of a gradient is 0. So that means that if A satisfactorily defines B, then for any lambda, a plus the gradient of lambda is also satisfactory. Okay, so that's the proof. That means that that's how a prime and a are related. If a defines b up here, then adding a gradient of a scalar field to a also gives the same b, just like our single variable calculus over here. So what we do then is we usually specify an auxiliary condition to lock down or to uniquely define a specific a. And what we do is we specify, we force, like I said at the beginning of this video, this is like a mathematical construct. We force a to have zero divergence. So that would be like in the single variable calculus, if I'm trying to specify one of these functions, I might specify just the function x squared. Force the constant to be zero. So I'm going to force the divergence of a to be zero. So again, because these are derivatives, the del operator is a derivative, taking the curl of a does not specify b completely. Excuse me, if we had b, taking the curl of a does not specify a completely. And similar here, the divergence alone does not specify a completely. But once you have the curl of a and you have the divergence of a, together the curl and the divergence completely specify a uniquely. So there's only one a that will give you this and this at the same time. Now, if you didn't quite grasp all of that, because like I said at the beginning of this pulls in a lot of vector algebra and vector analysis. That's okay. You don't need to know the details there, but I'm just giving the details there in case you're interested. Now let's move back to magnetic potential here, magnetic vector potential, this guy. So we can write so we've got this thing. Now, do you remember this? So what I've got, this was what we called del squared, right? And that was the Laplacian operator. So remember that the divergence, we're making the divergence of a equal to 0. So this has gone away now. And we're left with this thing here. That looks like Poisson's equation, right, from electrostatics. Remember in electrostatics we had this. That was Poisson's equation, right? Now we've got this. This is Poisson's equation, if you like, but for magnetostatics. But the big difference, and this should be a vector. The big difference is that this equation for magnetostatics is a vector equation. So this is actually like three equations, one in the x direction, one in the y direction, one in the z direction, whereas for electrostatics, V, the potential, was a scalar, and so this is just one equation. But you see, A now, this A vector, is playing the role of V, and so everything that we did for electrostatics here regarding the voltage, we can do with this new concept of magnetic vector potential. And just as we saw that V was the integral of dq over 4 pi epsilon r, okay, we're going to define A as an integral over mu 0 I dl over 4 pi r for line current, regular old current, or if we have a surface current, that we were using the variable k to represent that surface current. over 4 pi r surface current. And if we have a volume current, so in general, we would probably have a volume. In general, we say we have just a volume, and so that would be mu 0 j dV over 4 pi r for volume. Excellent. Now, one last thing. We're going to revisit, I'm going to just do this up here, magnetic flux again. So remember in the previous video that magnetic flux was defined as the surface integral of B dot ds. Now, because we're saying that B is the curl of A, we can apply Stokes' theorem, right? We can say that this thing is just this guy from our definition, and then from Stokes' theorem, which relates a line integral, a closed line integral to a surface integral, we have this. So this is another way of finding now the magnetic flux, like that. All right, so we're going to look at an example in the next video, and then from there we're going to move on to finding the magnetic fields, or studying magnetic material and the forces that that magnetic fields create on charges. So I'll see you then.